Welcome back and welcome to Unit 5. I'm mega excited for this. Because book 5.1 is so small, I thought I'd just tag onto the front of this video a little introduction of all of the different topics that are covered in Unit 5. So what's the structure of Unit 5 like? It's called the Newtonian World and Astrophysics. Module 5 is the only module which really feels like a journey, like you're going somewhere. We move from what we know and some really fundamental ideas that are required in order to understand the cosmology and astrophysics ideas that we talk about later. So take a look at the structure and you'll probably see what I mean. We start off looking at thermal and gas physics. We're going to be talking about stars, planets, atmospheres, that kind of thing. We need to be able to describe how gases work and importantly also what temperature is and how heat works. It's a really fundamental part of physics, so it'll be useful from here on in, but it's important to get those basics right before we move on. Circular motion is essential because, orbits and stuff, but also because it happens all around us. With circular motion oscillations, we go right back to the mechanics of it as well. We look at the forces involved, we look at the equilibrium of forces that we're in, we look at dynamics again, we use F equals ma. So you can expect to be doing loads of Unit 3 mechanics, as well as a bit of Unit 4 waves in oscillations and in circular motion. We then go straight into it and put those to good use in gravitation, planetary motion. So our number G gets a bit of an upgrade in this section. Gravitational potential equals mgh, that gets a bit of an upgrade. G is not constant. There's lots of other things to consider there. Planetary motion, so orbits and all of those dynamics. We spend 2 booklets looking at what stars are and how they work, because they are one of the main structures that we observe in the universe and they're essential to life on Earth. And we then move on to cosmology and have a look at how the universe works on a large scale, where it came from, what it looks like now, and where it might go in the future. So I really like Unit 5, especially because for you guys this will start to be where you piece it together and where you see stuff which before, it was just collisions, it's just a topic. They're now used in a much more interesting context, like they're used in gases and then that's used in stars. You'll see ideas from Unit 4, electronics and waves, put into the context of this much more exciting physics. It will go from now up until probably just after half term in year 13. We aim to finish circular motion by the end of this term. We might even make a start on oscillations. There's 2 books due this week, 5.1 and 5.2. Today I'm just going to talk about the key points to take home from 5.1. So let's get straight to it. 5.1 thermal physics. We're looking at solids, liquids and gas. Do not cast this book off as easy and stop learning it now, because you'll be one of those people that says the wrong thing and loses marks which are being given away to you if you use the right words. I'm going to start just with a little memory jogger for you, because I'm sure even if you hadn't done this book, ever since you were in kind of maybe even year 5, you could probably describe the difference between a solid, liquid and gas. What we'd have a look at in this book is what the difference is between a hot solid and a cold solid, or a hot gas and a cold gas, because that is the most important distinction. You've probably never been asked that question before, or if you have, it won't be that detailed a response required as an answer. It's quite important to be able to talk technically and using the correct language about the difference between these things. Have a little go at that exercise if you wish. So I'm just going to go through the book here. It starts off with the macroscopic view. That means the big scale view. Looking at something, how will I know whether it was a solid, a liquid or a gas? You know these things already, it's just there to remind you. A solid is resistant to changes in shape and volume. Okay, it doesn't fill its container and you can't squash them. You can try and change the shape, but it will just push back against you and resist that change. Compare that with a liquid. You know that a liquid will take the shape of their container, but have you ever tried to squash one? You can't change the volume of a liquid. You will always have the same amount. You can try and change the volume, but it will just push back against you and resist that change in volume. Gases take up shape and volume of their container. They will expand, they will change their volume to fill that container. Gases will change both, they do what they like. What's the most essential part of this booklet, I think, is the microscopic view, and in particular the wording. Here, there's a lovely table of things you need to know. It describes, in terms of the spacing, the ordering, and the motion of particles in each of the three states. What more do you need to know? Nothing, it's all here. In a solid, everything's close together. The ordering is regular, and the motion, as you probably know already, they vibrate about fixed points. Closely packed, regular arrangement, vibrate around fixed points. Easy. What people often don't quite appreciate yet is when we get to a liquid, people think there's like a closely spaced, middle spaced, widely spaced, and that's very easy. In fact, it's not like that at all. The spacing of atoms in a liquid is the same as in a solid. It is solid, liquid, gas. In fact, in some things in water, the spacing of atoms in a liquid is actually closer, but don't include that. The spacing is the same. Solid and liquid are just as close together. But Rob, liquids are clearly very different to solids. Yeah, they are, and it's because of the ordering. When we move from a solid to a liquid, the ordering becomes random. They're not bound to a fixed space. So they're still equally close, but they can move around. They're free to move and occupy whatever space they wish. Importantly, just make sure that you use the words here. So when you're describing a solid, closely spaced, fixed arrangement, vibrations. When you're describing a liquid, closely spaced, random, irregular arrangement, free to move. The easiest one on this table is gas. Particles in gas are very spread out, as you well know, and there is no order because they're always moving in rapid random motion. They are free to move and they move very quickly. More on that later. Say those words, get the marks. How do you know to say them? You need to commit time to learning them. And that's why I said on Tuesday afternoon, go and revise, go and learn this, commit it to memory, make your flashcards, make you memorise, make whatever it is that you're doing. Learn the stuff in that table, don't deviate from it, say it every time, and you can't go wrong. You'll notice that there's no questions in this book, and we've included some examples of what you might be asked below that table. So these standard answers are things that you should learn. You should learn to use this terminology, and you should not deviate from using specific technical language in your answers. If you say that waves bounce one more time, I will have a go at you. They reflect. If you say that motion increases one more time, expect us to have a go at you. What does it mean? Look at these. For a solid at a temperature well below its melting point, how do they move? They vibrate around fixed positions. That's what you say. We would ask a follow-up question like, well, what happens if I increase the temperature? What happens to the motion then? They still vibrate around fixed positions, but the amplitude and frequency of those vibrations would be larger. It's as simple as that. Do not say anything but the amplitude and frequency would be larger. I don't think I made that clear enough in my waves booklet, and that was why in the assessment before half term, many people were using absolutely rubbish words to describe waves. If you do not use the words frequency and you do not use the word amplitude, you will get 0 marks. Please just say the words that are in the book here. It's easy, it's the easiest way to say it. When you talk about liquids and gas, you would just say that the speed of that motion increases. The kinetic energy just increases, they move at a higher speed. There are a couple of important new ideas in this book. One is internal energy. Now, I think internal energy is most relevant when you see it used in the next 2 books. But we just introduce the idea here so that you start to get an idea of the types of energy that are at play here. The internal energy of a substance is the total sum of randomly distributed kinetic and potential energy of the particles in that substance. Those particles possess kinetic energy because they are moving. They might be vibrating, they might be sliding over each other, they might be whizzing around in a gas. And when you increase the temperature, you increase the kinetic energy because they travel faster or they vibrate with a higher frequency or amplitude. When it comes to the potential energy is involved in the binding of those together. So when you think about a solid, those atoms are bound into their fixed positions. The reason why they can't move is that forces hold them in place. It's potential energy that keeps those objects in place. So there's a lot of potential energy in solids because there's a very rigid, fixed arrangement. There's less potential energy in liquid because it's a more dynamic moving arrangement, there's no order, and there is much, much less, ideally no potential energy in a gas. That task just runs you through some of the things that happen. An important thing to remember is that heat always travels from areas of high temperature to low temperature. It does not travel the other way around because coldness is the absence of energy. Energy always tries to balance out so that it's the same throughout and we reach this thermal equilibrium. It does not move from cold to hot, it moves from hot to cold. Hence the picture on the front of the book. The final section of this book is just discussing some evidence. If I came up to you and said, hey, gases are made of invisible tiny particles that we can't see that move really fast, you might not believe me. So to show you where this model comes from and to demonstrate the fact that this model works, you need to be aware of one key piece of evidence. That key piece of evidence is called Brownian motion. And unless you're asked to describe what it is, you can just state Brownian motion as evidence for the particle model of a gas. So what is Brownian motion? It's when we look under a microscope at very small particles. Not microscopic, not atomic size particles, but things like smoke or, it's summertime, pollen, if your hay fever's kicking off. We can see these particles under a microscope. So if I take a sample of air with smoke or with pollen in it, and I look at how those little tiny particles are moving, what I observe is like this. We observe that they move with a random, haphazard motion. It looks like they're being hit by tiny things because they change direction very rapidly. It's almost a jittery motion. And the simple question is, why is this? As you can see in the standard answer there, Brownian motion provides evidence for this particle model of gas because it shows that these larger visible particles are undergoing elastic collisions with the molecules of a gas. If you think about it in terms of conservation of momentum, if you've got a heavy, large particle and a light, smaller particle, in order for that smaller particle to have an influence on the larger one, it must be moving faster. And so we have a read through that standard answer there. The movement of the pollen grains is caused by the molecules of the liquid moving in a random, haphazard manner. The pollen grains or smoke particles are visible, but the liquid or gas molecules are not. Hence, they are much smaller, and therefore we can assume they have a lower mass. Which means, one, that the pollen grains are continually moving, and it means that the other particles are continually moving. And two, something that's not written down there, and you might just want to add, is that it also shows that the speed of the gas or liquid particles is very high because their mass must be smaller than the larger pollen grains. The type of path that you see, so if you look at the GIF again, this type of path is known as a random walk. Random walk is a quite common type of motion, and for that reason, that key word should be used, especially if you want to really impress an examiner. If you describe the path that they take as a random walk, they'll know what you mean. I hope that it's fairly obvious that if you increase the temperature, you would increase the speed of all of these things, and therefore you would expect the particles to move around faster. But also, the thing that people always forget, if everything's moving faster, you'd probably experience more collisions as well. So I hope that's a very brief summary. The main point that I want to make for you guys is do not stray from the terminology used in the book. This specific technical vocabulary is required of you. Actually, it's because if you're going to be a real physicist or a real engineer or a real scientist, you can't use these big sweeping statements like they see on TV or like YouTubers say on their science channels. They're just not technical enough, they're not precise enough. The language of industry, the language of research, the language of academia, where you're going to go next, demands really, really precise technical wording. and that is why you must say things like the amplitude increases and the frequency increases. I hope that's useful, and later in this week we will look at 5.2. Here's a little recap for you just to piece everything together.